So given that the same knot can have sort of infinitely many different diagrams that can represent it, we want to reclaim diagrams somehow. We want to see them as something that's intrinsically valuable. We want to be able to study knots using their diagrams. But in order to do that, we're going to have to get a little bit more specific about how all of the different diagrams for a given knot, what all of them have in common, what all of them must have in common. Any property that all of the diagrams of a given knot must have in common is called a knot invariant. And so knot invariants for us today are going to be our goal, the thing that we're going to try to get to. And so to get us a little bit closer to knot invariance, let's start by studying the simplest knot in the universe, called the unknot. The unknot, by definition, is any knot which has a diagram with exactly 0 crossings in it. So as you might imagine, an unknot probably looks something like this, right? It's not knotted whatsoever, and yet it still meets the mathematical definition of being a knot. So go figure. But we call it the unknot because there exists a diagram of it that has no crossings in that diagram whatsoever. Of course, there exist a bunch of other diagrams for the unknot that have multiple crossings in them. Like here's one such example, right? I didn't untie this thing to make this diagram. I just took my unknot in space and I just sort of bent it around a little bit, smoothly changed it from one place into another place, perform what we came to know in a previous week as an isotopy, right? An isotopy of a knot is just any way of sort of pushing it around inside of three-dimensional space without breaking it, without untying it and retying it. Whoops, this one just came apart. But you get the picture, right? So clearly, I can make really complicated diagrams of an unknot just by taking an unknot and sort of wadding it all up, making its arcs and crossings all over the place. I start with a big unknot. I can do a lot of different stuff to make a more complicated diagram for myself, right? I can loop this thing around itself a bunch of times, can create a whole bunch of arcs and crossings that we didn't have before, right? And you could imagine that if I sat down and I sketched out a diagram for this thing that I'm looking at, it's going to have, I can barely even count, maybe like 12 crossings or something, and 10 different arcs, who knows, right? And so the question, of course, is if you gave me that diagram, would I be able to tell that in fact it was the diagram of the simplest knot in the universe, the unknot? So this is going to be an opportunity for you and your team to kind of take that wadding up process that I just did, that can make a diagram more complicated, and make it a little bit more systematic. So in this activity, what I want you to do is start with an unknot. And this one really does work best if you have a physical copy of the unknot in front of you. And perform an isotopy on your knot to discover and sketch a diagram of it that has exactly 1 crossing. So that's where we're going to start, right? Go from 0 crossings to 1 crossing and sort of describe what it was that you did. What isotopy is it that accomplishes that? Then return back to the beginning and perform an isotopy to discover and sketch a diagram that has exactly 2 crossings. So what isotopy would result in adding 2 crossings to your diagram? And then, this is probably the trickiest one. What I'm asking you to do here is to return to the braid relation back from section 2.1. That was this formula here, the SI plus 1, SI equals SI plus 1, SI plus 1. This was the tones to notes braidogram that we had in the very first chapter. Back in activity 2.1.2, you came up with that braid relation. So go back to your tones to notes sketch and see if you can figure out what isotopy of a diagram for a knot, for example, would be used to establish that. This one's going to be a little bit harder to describe, so sketching pictures of it is probably the best way to do it. So start with a diagram of your unknot that has 3 crossings or more in it, and see if you can figure out how to use that tones to notes 3-strand isotopy to change the diagram in a meaningful way, but not actually change the underlying knot that's underneath it. So in this exercise, you're just coming up with 3 different ways of manipulating your knot to either add a crossing, add 2 simultaneous crossings, or to sort of manipulate a region that has 3 crossings in a way that reflects that braid relation. So I want to give you a good 15 minutes to do the work on this, and then we'll come back and discuss what you found. But this ties right back into the discussions we had about braids and the discussions we had about permutations. So definitely do look back at your responses to those activities as you're doing this one. So the task was to start with an unknot and then figure out some ways of adding either one crossing or two crossings to this diagram without changing the fact that we're looking at a diagram of an unknot. So the first thing that you notice is that there's a quick way to add a single crossing. It's just to kind of do this, right? Make a little figure 8 loop like that. We do that, we get a new diagram of the unknot that has a single crossing in it. So I think that we can agree that if ever we see something that looks like this in a diagram, we can simplify that diagram without changing the knot itself, just by kind of untwisting that knot, right? And ending up with a diagram that has fewer crossings than it did before. So this is one way that we can kind of add or subtract a crossing from a diagram. It's just to create one of these little loops. There was an interesting thing that happened on the second part where I asked, how can we create a diagram with two crossings instead of one? Because certainly one way to create to create two crossings in an unknot is just to do this thing that we did to create one crossing and then just do it again. So make a loop and then make another loop. Let's see if I can get this to actually lie down here. Of course, this shoelace has like a permanent kink in it, so it really doesn't want to cooperate. Maybe if I do it sideways. So create one loop and then create another loop. Yeah, there we go. Nope, it doesn't want to do it. All right, I'm going to use the beautiful diagram that your team number 2 here sketched. So this diagram here in part A, this is one way to do it. Do 2 of those same twists in a row. We create 2 crossings only by doing that same maneuver that we did to create one, just doing it twice in a row. But there's another and fundamentally different way of achieving the same end. And this is the other team's diagram of what that looks like. In this example, what we're really doing is we're doing a twist in one direction to create a new crossing, but then the second twist that we add, we're doing kind of in the opposite orientation as the first one. So in total, what we're kind of doing is making a little sheet bend in my knot, and then just sort of pushing that sheet bend across one of the other arcs in my diagram. So that what I'm looking at here in my diagram is kind of 2 crossings that both kind of look like overs, or they both kind of look like unders in a row. In this example, if I look at the east to west strand in my diagram, that east to west strand is passing over and then over again the crossings that it's encountering, right? And so if I look at this, I can say, well, I can remove both of those crossings at the same time just by performing an isotopy that looks like this. Just slide out the underneath strand from the strand that was going over it, and now we have our 0 crossing unknot back again. So that is a fundamentally different way of creating or destroying 2 crossings at the same time, besides just creating one crossing and then doing that same thing to create a second crossing. So that accounts for the first 2 of these diagram maneuvers that we can use to simplify a knot diagram. If I ever see a place on a knot diagram where we have a figure that looks like this, where we have 2 crossings that are both overs or both unders in a row or something like that, then we can simplify that diagram just by sliding that sheet bend out from underneath the other one. And so the tricky one of the bunch is the one that I was trying to get us to get to in question number 3, which is, what does the tones to notes braid relation, what can that kind of tell us about diagrams for knots? So back when we first were talking about positive braids, we were able to convince ourselves that the braid diagram on the left here, which exchanges the first and third positions in a 5-strand braid, right? The T and the N trade places in the word tones, and we get notes at the end, and we make it all into a positive braid. And we found out that this diagram on the left and this diagram on the right really should represent the same braid. There should be an isotopy of braids that connects this one to that one. And the reason is that there's this one strand, it's the T strand, which is lying on top of both the O strand and the N strand that are underneath it. So if I could just grab a hold of this T strand and slide it to the south and west and slide it to the other side of this ON crossing, I'd get a new diagram that looks like this one. The T strand is still passing over the O and the N strand, and the ON crossing is still a positive crossing, right? But when I read the braid language for this, I'm seeing S2, S3, S2 in the first case, but S2, S1, S2 in the second case. No, I guess it's 1, 2, 1 and 2, 1, 2. Sorry. So the braid language is different, right? But there is an isotopy between these two braids. So what might that look like with our unknot? This was the tricky part where I was trying to get us to, and I just don't think I need to maybe phrase this question differently in the future. But I think the closest that we got is one of your teams figured out we can make a diagram of the unknot having 3 crossings. It looks an awful lot like the trefoil. And one way that we might do it is by first creating a single crossing by doing the thing we did in part 1. Just make a twist. And then I can sort of take this, loop it under itself, and pass it underneath the other bend over here. So what I get here, and of course I'm still fighting against this permanent kink in my shoelace. See if I can straighten it out a little bit. So again, we make a twist to create a single crossing, and then we sort of pull that loop underneath the opposite side. So we're sort of sticking together a move of the first type with a move of the second type. And so we get this new diagram. All right, this looks kind of like what we're trying to see here. We get a new diagram that has 3 crossings in it. It looks an awful lot like a trefoil, but we know it can't be a trefoil because I didn't untie and retie this thing. I just started with an unknot. I created 1 new crossing by using the first move. I created 2 more crossings by using the second move, and I get this diagram. I'm going to try and work with the sketch that Team 2 used for this situation here. So in the tones to notes example, what we were doing is taking a string that lied over 2 other strings and just sliding it back over to the other side of another crossing, right? So I'm going to try and notate that on this diagram. I'm going to take this strand right here, this over strand, and I'm just going to move it over to the other side of this crossing. I'm just going to pull it out. If I were to do that, this crossing is now going to be on the other side of that strand. So let me try and sketch that crossing in first. So it's got kind of this geometry going for it. But now my red strand has moved over to the other side of it. Yeah, I think I can just use it that way. Right, so my old red is now my new red over here on this side. And so, again, all it took was to do an isotopy. I just took one of these over strands and just moved it back over to the other side of its adjacent crossing. And I ended up with something that only has this 1 twist in it. And so, I guess actually I moved this a little bit too far. Let me try and draw this in a way that illuminates hopefully even a little bit more what I'm trying to communicate here. If I were to really do this the way that the diagram kind of shows, here's what would end up happening. I would end up with something that looks more like this. Nope, it's an over. Sorry. I'll get this right one of these times. So it needs to be an over strand still. So it would look something like this. No, because I also need a loop on this side. There we go. So this is more what I had in mind. Because we both begin and end with a diagram that has 3 crossings in it, right? The only thing we're doing is we're moving this one arc from the left side of this crossing over to the right side of this crossing, right? And so it still has 2 more there's still 2 more crossings with these arcs after we move it over to the right. But all we're doing is moving the location of that strand. Start with 3 crossings, end with 3 crossings, but we've pushed this red strand, the over strand, from one side of this crossing over to the other side. But now in this format, I think it's easier for us to see why this thing actually is an unknot. If I wanted to unknot this diagram over here on the right, I can notice that each one of these 3 little loops is just an isolated loop of the kind that we sort of convinced ourselves in the one crossing example was a trivial matter, right? This one single little loop with itself is something that we can always just kind of untwist. So if I wanted to actually untwist this diagram, all I would have to do is kind of untwist each one of these by itself. And that would give me 0 crossings left, right? So what's the point of all of this work that we just ended up doing? The point of all of this is that we discover these 3 different moves that we can use to change the diagram of a knot that actually correspond to isotopies of that knot. And so they're not actually changing the knot itself. They're just changing the diagram. In one case, they're changing the diagram by either adding or subtracting one crossing by just doing this little twist or untwist maneuver. This was the first example that you did. This is called the twist move, or sometimes it's called the type 1 move, that either adds or subtracts one crossing from the diagram. The second, where we make this little sheep's head and then pass it underneath or over an adjacent strand, right? This is called sometimes a poking or an unpoking maneuver in a diagram. It adds or subtracts 2 crossings, but it doesn't change the knot because it's an isotopy, right? That's called the type 2 move. And then this third one, this was the most challenging one, the one we just finished talking about, doesn't actually change the number of crossings, but it can move an arc which passes under or passes over both of the strands of a certain crossing from one side of that crossing to the other side. We call it a slide. It doesn't change the number of crossings in the diagram, but sometimes it can make the diagram simpler to understand, as it did in this example, where we started with something that looks an awful lot like a trefoil, but after we do that slide maneuver with this arc and push it over, now all 3 of my crossings are isolated. All of them are just single twists that we can then use a type 1 move to untwist. So these 3 diagram maneuvers are ways of changing the diagram of a knot without changing the knot type itself because they correspond to isotopies. They're called the Reidemeister moves. Type 1 move, type 2 move, and type 3 move. And we can use them to simplify diagrams, to reduce the numbers of crossings, to try and understand what is the simplest possible numbers of crossing for a diagram. Or sometimes it's possible, sometimes it's useful to actually use them to add crossings, because sometimes that actually helps to illuminate the structure of a knot later on down the line. But what's wonderful about the Reidemeister moves is that the main theorem that Kurt Reidemeister proved in 1927, he was one of 2 mathematicians who proved this result kind of within 1 year of each other, and somehow he got it named after himself, and I don't remember what the other folks were named. I can look that up. But what he proved is that these 3 moves are in fact the only ways of changing a knot diagram that correspond to isotopies of that knot. In other words, any 2 diagrams of the same knot will be related to one another by some combination, some sequence of just these 3 moves. So if ever in doubt with whether 1 or 2 diagrams of a knot represent the same knot, they represent the same knot if I can change one of those diagrams into the other one by doing some sequence of these 3 maneuvers. I might have to do a lot of these maneuvers to do it, and it might be impossible for me to tell which ones I need to do in which order. This is a very computationally difficult problem. But Reidemeister's triumph here is showing that even if it would take a computer a million years to compute it, any 2 diagrams of the same knot could be said to be the same diagram of the knot because they would be related together by some possibly long sequence of these 3 maneuvers. So this is the open and shut case. These are the only ways we can change knot diagrams that correspond to isotopies of that knot, and so they represent the same knot.